because of the fact that industry uses such large quantities of power, if you were to supplant a large portion of that with electric use, the ability to deliver that electricity needs to be increased multiple times. Do we have the capabilities to do that? I would say the answer is clearly no in this case. And it's not only the supply lines from renewable energy sources, but it's also the facilities at site. So that's transfer stations, for example, to be able to supply the electricity reliably. One of the other point that's really important to consider is that industry has got to have reliable power, reliability better than 99.99%. So how does that intersect with variable sources such as wind and solar? Well, that's a big question. There are some chemical processes that are intermittent, but very few. Most tend to run in continuous fashion. So that's where storage can come in, such as thermal storage or, of course, pumped hydro in the US accounts for more than 95% of renewable energy generation. But not every place has pumped hydro facilities nearby. So I think storage will need to be one of those areas that needs additional research to figure out how to address that variable component. So good questions.
Okay, thanks. Interesting answers. Yeah, well, I think most people would agree that getting electric power there is a big issue. And particularly if you look at these kind of big demands like electrification of crackers or steam reformers or things which really require multiplying the electricity demand by a factor of 10 or something, then
right. And you mentioned
infrastructure. Yeah.
You mentioned crackers there for ethane crackers, the ethylene. At a small scale, electricity is used. So lab or bench scales use electric heating. Why is it that it's not used at the really large scale? Well, there's some research that's starting. There's a collaboration in Europe. And Dow Chemical and Shell have another collaboration going on in that space. But the challenge is scale up and the efficiency of that electric power use at really high levels, at really high temperatures. That's yet to be determined how to meet those needs.
Yeah, okay. I think someone's about to say something when I started speaking. Did I miss something?
Yeah, this is Ammi Amarnath, Simon. I just wanted to add to what Ed said in terms of availability of electric power. You know, there's quite a bit of push. I understand for very large, focused use of electric power, there may be issue. But in general, there is such a push for renewable power generation on the distributed scale and kind of connecting the system, just like how we connect internet systems today. Have a connected grid is a lot of work going on around the world, I should say, in terms of making renewable resources much more applicable for even for industrial processes. Just wanted to make that comment.
Okay, I have a question here for Jibran, asking if you looked into industrial clusters or if your work was mostly focused on individual plants.
Actually,
interchange between plants.
So it was not really focused on individual plants. There was just one study to see if the potential in that individual plant somehow is in the same ballpark, which the same ballpark of the energy efficiency improvement potential at the macro level. So I basically followed a top-down approach to estimate the excess heat levels and identified the clusters. But now we are studying that, okay, how we can potentially use this industrial excess heat for district heating systems, and then I have also plans to consider this resource for inter-industry cascading, heat cascading. So no, we estimated it. We estimated the potential for each clusters from the top-down approach, but we didn't go via individual plants. It's too much work, and there are thousands of plants. So it is certainly not possible to do a pinch analysis for all of them and then estimate a integration potential.
Okay, well, thanks a lot. Let's see, if we come back to Ammi, there's been, you had a question which you answered, but maybe you could comment a bit on your answer. The question was that air-cooled chillers, they may well save water, but the water-cooled chillers are inherently more energy efficient. And so the question was, in terms of the cost savings, which is ultimately probably what decisions will be based upon, which is better. And your answer was, well, you agreed about water-based heat exchanger efficiency benefit or advantage. And you said there's some work ongoing for the cost effectiveness. Maybe you want to comment a bit on that?
Sure. Thank you, Simon. Again, it all depends. In some areas in the world, we have lots of water. In some areas, let's say California, we have a deficiency in water. So it's really a trade-off between energy and water. And actually, we are doing quite a bit of work in this whole area of energy-water nexus. So the cost effectiveness of water versus electricity needs to be looked at, especially in areas that have got deficiency in water. And what we see at EPRI, since we are doing quite a bit of research on the power generation side, having water, availability of water for power generators, classic power generators, is becoming an issue around the world. So things like dry cooling and all is being developed. So cost effectiveness all depends on the cost of water and the cost of electricity. I should say that in my area, at least in my house, I pay almost as much for water as I pay for electricity. Okay, so saving of water has an enormous benefit here in California and other parts of the country that do not have as much water. Okay, however, our report will show the cost effectiveness of air-cooled versus water-cooled chillers. It'll come out in the final report. I don't have that information right now, as far as this specific project is concerned.
I can easily understand that saving water is a big driver in California and other dry areas. A follow-up question, which is more about the technology. You showed that very substantial improvement of the COP there. And basically, on the technology side, you're introducing two things at the same time, right? You've got your microchannel heat exchanger, and you've got that semi-hermetic compressor. So you basically got two new components in there. I think in the paper you really discussed how much of that improvement of the COP can be assigned to one and how much the other. Any comment on that? Where you think?
Oh yeah, I mean, I would say that a majority of the improvement. Well, I mean, the improvement in COP is a function of many things within the machine and how it is designed. So I wouldn't want to go into the details of which part of which equipment improves the coefficient of performance or the efficiency. Obviously, microchannel heat exchangers play a very big part in improvement of efficiency. We know that. Okay, they play. The semi-hermetic compressor that is used, which has got aluminum windings, ammonia is in that, and you don't want explosions or leakage of ammonia to happen, and that's how we are able to reduce the amount of ammonia that is being used in the system. Okay, so I would say, if I had to kind of think about it, microchannel heat exchangers offer the COP improvement. Semi-hermetic compressors improve the usage of ammonia or lower the usage of ammonia in this particular application.
All right. Okay, yeah, well, I can see you've done many things there and you've been tweaking on many fronts, so it's maybe hard to say this is the number one. This is the one which is really making the difference and the rest is fine tuning. I understand that you probably need a lot more research or detailed measurements to be able to break that down.
That is absolutely correct. I mean, there are many other things also in the machine. I mean, the footprint of the machine, the way it is, it's designed. I mean, the chiller is, this chiller is probably half the size of the 507A chiller for an equivalent capacity. Okay. So all of these things make a difference, newer type of motors, newer type of windings, and so on and so forth. So.
Okay, neat, interesting reading. Let's see, Jazaer, you showed some fairly amazing numbers, saying, if I got you right, 50% of final energy use is related to electric drives. Was that, or even 55? Is that correct?
Yeah, that's true, and that's a prediction. So it's not something that we have already today, and that is when we will be able to use that huge number of sensors for the electric motor systems and fans and pumps and compressors. Given that the numbers that I showed in the table, that will be that numbers, so to say.
I thought that was actual statistics. This is how
exactly. Yeah.
Used.
And also I put the link for the study that calculated or did this prediction for the future, for the coming 10 years in the slide. So, but if it's not that amount of energy, it will be perhaps a little bit less or even more. Who knows? I mean, it's very much depending on the development in the sensor technology. And it has been really very rapid development last years. It's extremely promising now when they are even getting smarter than what they have been lately. So the combination of the sensing technology with AI is extremely interesting, and that will be, of course, a great energy saving if they by their own get that smart that they can make a decision, and if we also include the energy saving that come now we are focusing on energy efficiency of the systems, but also we do have saving in maintenance and failure predictions. That's additional energy saving, but our task or our focus is on energy efficiency, but indirect it's going to be energy efficiency, of course. So maybe in the future, if the development proceeds as it's today and even more, then I think we are in a very good condition in the coming 10 or 20 years.
You said a 5 to 10% potential savings, but that's
yeah, 5 to 10%. Yeah, of the global electricity
use. That's a huge number.
Yeah, it's 5 to 10% of the global electricity use in electric motor systems, and we know that they use a lot of electricity. So it's a great amount of energy that can be used. And this is why we are interested in this particular topic, because we know that there is a great potential for efficiency, energy efficiency in electric motor systems. It's maybe it's not prioritized that much for some reasons. Some of the companies are aware of that, but some have other priorities. So to make them aware of the potential is one important task, of course, for us and everyone working on this topic. But let's see, things are progressing.
Right.
This 5 to 6% potential, does it correspond to only motor replacement and variable speed drives, or it also includes good practices like leak repairs and optimized hours of operation and all these kind of things?
I'm not sure that I hear you properly. Can you please repeat your question?
So I'm saying that this 5 to 6% potential that you mentioned, is it corresponding to only motor replacement, and variable speed drives, or it also includes these good housekeeping, yeah, or energy management practices like
Yeah,
hours of operation should be optimized, or leaks should be repaired, or things like that.
of course, many of things you are mentioned. So 5 to 10% of global end use electricity, it's 5 to 10, but in terms of energy units, it's 50 to 100 terawatt hour per year. And when you make the, now I don't have these details, it's given in the report, of course, but when it comes to energy efficiency, it's a lot of things that you can work on to make them more efficient. So for sure, if not all, but some of the things that you mentioned are included.
I asked this question because I also did a study in my thesis on motor systems, and for Switzerland, I estimated something like 17%, which is much higher. So
Yeah.
that's why I was wondering why it is so low.
Yeah, I mean, yeah, of course. It depends also very much in many cases, you know, they are not optimal from the beginning, that the installment of the motor in industry is not very optimal. They go for the worst case, so to say. So maybe most of the systems are not working at the optimal points, as you know. Mm-hmm. So already there is a potential for a lot of energy saving, and in addition to many other parameters that could be used for the saving. Now I don't have the details to answer your question properly, but for sure it's in the report.
Mm-hmm. Okay, thanks.
I think you made the point that you went through a nice overview of barriers, and one is that electric drives, they kind of last forever.
Yeah, exactly.
And
this is a major problem.
To change to something that works, even if it's not as efficient as it could be. Do you see any opportunities for speeding that process up? Or?
Yeah, it's like to make the awareness in the industry, because even though they have invested, they of course it's a huge cost. Once they have invested in these electric motors, they will not be replacing them, but like helping them to calculate how much the energy cost is and how much they could save during this lifetime. Maybe that will alter a little bit the view they have, but it's very difficult. So it's a lot of work need to be done there to convince, and it's also a management thing. So also maybe there are also opportunities to do something with already these old-fashioned motors. It's not completely impossible to make them more energy efficient. Like maybe it's not possible to install sensors or so, but some small steps can be done to improve their efficiency. So it's very difficult to replace them when they have like 20 years left of their lifetime.
Exactly.
Yeah.
Okay, well, the time is more or less up. Let's see. We have one last question here, which just popped up to Jibran about how you identified the final heat exchanger network in the textile plant example with the batch processes. If you combine pinch analysis tools with other optimization tools. If you would like to answer that before we wrap up.
I'm not fully sure if I understand the question. So how did you identify the final heat exchanger network in the textile? Okay. So the thing was that, as I mentioned, that there were no fixed schedules in the textile plant. So I had to divide the daily operation into 7 time slices. And for each time slice, I was analyzing that, okay, which equipment are in operation. So my priority was on those equipment which were part of the same process. So for example, if the fabric needs to be dried, so I violated the rules of pinch and always made sure that the stack of the dryer should be exchanging heat with the inlet temperature, inlet process water. So, and the penalty for this is what you see in that remaining 30% potential. So that's the thing. That's the problem with batch processes, and especially when it is a multi-path, multi-product batch process, when there are no fixed schedules and the operation is based on customer orders. I mean, the conventional pinch analysis simply cannot be done. I mean, it can be done, but for the heat exchanger network, you cannot come up with a simple solution. So yeah, that's the thing.
Okay. Okay, well, I think we will leave it at that. I'd like to thank all of our speakers today, for their presentations and for their joining in the discussion here. Thank the audience for coming up with some good questions, which kept the session on the run. That's it for panel 4 today. Tomorrow we actually have 2 sessions, so both at the 12 noon and the 2 o'clock session. Sorry, no, my mistake. We just have a panel 4 tomorrow, just 1 session at 12 o'clock. And Anna will be handling that. So thanks to all of you, and look forward to seeing you tomorrow. Thanks again.
Thank you.